Hi everyone, this is Chihuang Zhang. In this video, we are going to talk a little bit more about the odds ratio. We are going to talk about the property of the odds ratio and its implication in associations. The odds ratio is defined as the ratio of two odds in a comparison between Group A and Group B, where Group A is the group of our interest and Group B is our control group. In the class, we learned how to calculate the odds ratio of being happy for Cheeto on a sunny day versus a rainy day. We first determine what is the comparison in the study, and then calculate each element in the odds ratio separately. In this 2x2 table, the odds ratio is 6.67. So what if we switch our variable of events and the variable of comparison? Say, what is the odds ratio of a sunny day for a Cheeto in a happy mood compared to a Cheeto in a sad mood? If you're following the same process of the calculation of the odds ratio, you will realize that the odds ratio for this case is actually the same, which is still the 6.67. In fact, this equivalence is not just a coincidence. To make it clear, let's substitute the value in each cell of the 2x2 table using letters. For the first statement, we compare the different weather where we calculate the odds according to the conditional distribution on the rows of the table. For the second statement, on the other hand, we are comparing the different moods, and hence we'll calculate the odds by looking at the columns of the table. And mathematically, these two odds ratios are exactly the same because we can express them into the ratio of the product A and D and the product of B and C. Here, the numerator is the product of the diagonal cells, and the denominator is the product of the anti-diagonal cells. When we discuss the relationships of the quantitative variables, we mentioned that the correlation coefficient R is symmetric in the sense that its value will be the same if we switch the exposure and the outcome. And here, when we talk about the categorical data, the odds ratio also has the symmetric property, since the value of the odds ratio will be the same if we switch the exposure and the outcome. And that is why we use the odds ratio to describe the correlation between two categorical variables, rather than using the relative risks. Similar to the correlation coefficient, the odds ratio can tell us both the direction and the magnitude of the correlation. The direction of the correlation is given by comparing the odds ratio with value 1. If the odds ratio is greater than 1, it means that our event of interest has greater odds of being correlated with Group A than Group B. In our example, the event of interest, which is happy mood, has a higher odds in sunny days than the rainy days. If the odds ratio is smaller than 1, it means that there is a lower odds of association between the exposure and the outcome. In our example, we would expect that the happy mood of the cat has a larger odds in our control group, which is the rainy days. If the odds ratio is 1 or approximately 1, we would expect that two random variables has no correlation. The strength of the correlation is determined by how far the odds ratio is away from 1. As the odds ratio increasing or decreasing from 1, we would expect the correlation will be stronger. If we look at the formula of the odds ratio, the conclusion implies that the correlation will be strong if A times D is much larger or much smaller than B times C. In terms of the 2x2 table, this scenario is reflected by the case where the diagonal values of A and D are much larger or smaller than the anti-diagonal values B and C. And this is why, in the previous lectures, we can get an intuition about the association just by checking if the large values are located on the diagonal cells. In a study of the correlations among the categorical variables, there will be an interesting phenomenon that could happen called Simpson paradox. Simpson paradox refers to An association that appears to hold for subset can reverse the direction when the data are combined into one group. So let's take a look at the following example, where we are trying to study the correlation between the smoking status and the death. If we directly calculate the odds ratio from this 2x2 table, we will get an odds ratio of 0.81, which means the smoker has better odds alive than the non-smoker, which is quite counterintuitive. This is because this study is actually strongly confounded by a third variable, age. If we separate the data according to the age group and create 2x2 tables according to each age group, after calculating the odds ratio, we can see that the odds ratio in all groups are in fact greater than 1, which means the smokers has less odds for life than the non-smokers. In the previous lectures, we have seen that ignoring the confounding variables will lead to a fake correlation. From this example, we can see that the confounding effect can also end up with an entirely opposite direction of the association. Therefore, we can consider Simpson paradox as an extreme case of a confounding problem, where the direction of the association is reversed. Thank you for watching the video for today, and I'll see you the next week. Bye.